In the very first week of Calculus 4, I mentioned a problem to you. That is, well, this looks like a very friendly problem. Try to find the minimum value of this objective function subject to a very friendly constraint. However, the issue is, if you try to do this but by the method Lagrange multiplier, it does not give you the minimum value, because the minimum value actually happens at the origin. But the origin is not captured by the method Lagrange multiplier. The reason is that because Lagrange multiplier is based on a geometric argument that grad f and grad g are parallel. However, this argument only makes sense when grad g is not the zero vector. However, in this case, well, grad g is indeed a zero vector, so it does not make sense to say parallel to it. So this is what I call a degenerate point at that time. And now we're ready to properly define and also handle, capture all these degenerate points. And this is what we're going to do. Now let us get back to the notes of this week. The next section is called Non-degenerate constraint qualification, or in short, we call it NDCQ. Okay, NDCQ. So what is it useful for? This is to tell us whether exceptional, or we call it degenerate, points exist. Okay? In particular, we say that an optimization problem passes the NDCQ if no such degenerate point exists. Let us look at definition 12.2.1. Let me put a star here. This is very important. Okay? And then we're going to consider the optimization problem as before. In particular, the constraint set is given by G1 of x1 to xn equals to a1, and then you have k of them, gk, x1 to xn equal ak. Okay, this is the set of constraint. And then what does it mean by a point to be degenerate or non-degenerate? So this is the definition. A point P from the constraint set, this is very important. So you don't take an arbitrary point, you only take a point that satisfies this collection of constraints. And then this point is called non-degenerate, or it satisfies the NDCQ if the matrix, okay, this matrix, what is this matrix? This matrix, the rows are given by the grad of the constraint functions. Okay, you put all, well, you have this constraint function g1 up to gk, you take the gradient and then put them as rows. And then you have k rows, okay, because you have k constraint. And then if this matrix has rank k is exactly the number of constraints, then we say that this point is non-degenerate, or is, well, or we call it satisfy the NDCQ. Okay? And then what does it mean by an optimization problem to satisfy the NDCQ? So an optimization problem is said to satisfy the NDCQ if every point from the constraint set satisfy the NDCQ. Okay? So we define what it means by a point from the constraint set to satisfy NDCQ. That is by looking at the rank of this matrix. And then if every point from your constraint set, or every point that satisfies this collection of equations satisfy NDCQ, then we say that the entire optimization problem satisfies the NDCQ. Okay? And then just one piece of terminology. So this matrix here, formed by gradient of the constraint function, we usually call it Jacobian matrix or Jacobian matrix. Just a name, okay? I will seldom use it. But in literature, this is called Jacobian matrix. It's actually very related to the Jacobian that you learn in Calculus 3, but I don't want to pursue it further here, okay? So let's do some examples. So example would be much more helpful for you to understand what it means by NDCQ. So let's look at this. So verify NDCQ is satisfied for the following set of constraints. So I give you two sets of constraints. So A and B. Okay, let me put a line here. So A. Firstly, part A. Part A, we're given two relatively easy constraints, 3x plus y per set equals to 1, and x plus y per set equals to 2. Okay? And then how do we determine whether a optimization problem or a constraint set satisfy the NDCQ? We just need to make sure that every point satisfying the constraint satisfy the NDCQ. So let P equals to xyz be a point that satisfies the constraints. So I didn't do anything, okay? I didn't do anything. I just pick a point that satisfies the constraint. I need to make sure that this point will satisfy the NDCQ, okay? But to do that, let me give the constraint name. So for example, this one, I call it G1, okay? And this one, I call it G2. And then to check NDCQ, we need to look at the Jacobi matrix or Jacobian matrix. Jacobian matrix is formed by, putting gradient of the constraint function as rows. Gradient of G1 and gradient G2 as rows. But then in this case, you realize that, if you, take the gradient of G1, what do you get? You get 3, 1, 1. Okay? So this is gradient of G1. How about gradient of G2? Well, gradient G2 is given by 1, 1, 1. And then what about NDCQ? We need to make sure that the rank of this matrix equals to the number of constraints, i.e. 2. So, what's the rank? We learn how to find rank by Gaussian elimination. So, if you turn this into REF, then this will become 1, 1, 1, and then minus 2, minus 2. And then this REF. And then in particular, there's no 0, so, therefore, it has rank 2. Right? So, we take an arbitrary point that satisfies the constraint, and then we discover that the Jacobian matrix has rank 2. Therefore, P satisfies the NDCQ. And because P to begin with is arbitrarily chosen, therefore, in this case, the optimization problem satisfies the NDCQ. Because here, P is arbitrary. Okay? So I'll probably write down more than enough what you need to write in the exam. However, I want to make it very clear here how this argument works. Let's do a slightly more complicated example. Part B. Part B. This time, you're given two constraints, x squared plus y squared equal to 1, and x plus z equals to 1. So as usual, we let this to be G1, and then let this to be G2. And we need to check every point that satisfies the constraints will satisfy the NCDQ, So, then to begin with, we let P to be xyz be any point that satisfies, let me just say the constraints, Sorry, I keep misspelling constraints, And then to check NDCQ, I need to consider the rank of the Jacobian matrix. So Jacobian matrix in this case, okay, so the first row, come from taking the gradient of the first constraint function. So G1, when you take the gradient, you get 2x, 2y, and 0. So this is grad of G1 at point P. Okay? And then whereas the second row come from taking the gradient of G2. The gradient of G2 is 1, 0, 1. To determine the rank of this matrix, we have to transform it into REF. So REF. So if you do it, if you transform it into REF, you get 0, 2y, and minus 2x. Okay, I will let you to check. But you need to be careful here. That is, it's not clear whether this matrix has rank 2, because it really depends on the value of x and y. Okay, so you may ask, is it possible that this is a 0? Because if this is a 0, then this matrix will have rank 1, then NCDQ will be failed. Okay, so let's see. So for this to have rank strictly less than 2, we need 2y equal minus 2x equals 0. So that means that x equal y equals 0. But is that possible? X equal y equals 0? Of course not, because, well, xy set is come from the constraint set. So in particular, it satisfies x squared plus y squared equal 1. So therefore, x and y cannot be simultaneously equal to 0. So let's say, okay, however, a point, so P, if x and y are 0, this does not satisfy one of the constraints, okay? Because one of the constraints is x squared plus y squared equal to 1. And this is a contradiction, okay? This is a contradiction. What is the contradiction? It contradicts with the fact that you try to assume the rank to be strictly less than 2. So hence, this is impossible. That means that the rank is always equal to 2. Because if the rank is strictly less than 2, we have a contradiction. The rank equals to 2, which is the number of constraints, therefore, P satisfies the NDCQ. Okay? And then hence, because P is arbitrarily chosen, because P to begin with is any point from the constraint set, so that means that the optimization problem also satisfies the NDCQ. So don't be too scared even you manage to find some value of x and y such that the Jacobian matrix has ranked strictly less than 2, because those points may not be come from the constraint set to begin with, okay? For example, in this case, you realize that, well, for this to have rank strictly less than 2, you need both x and y to be 0. However, this is impossible, because one of the constraints say that x squared plus y squared equals to 1. So there's no such point. So therefore, this thing is always of rank 2. That means that NDCQ is satisfied. Okay, now let me look at an example for which NDCQ fails. Okay, so this example. This indeed comes from the example from week 9. Okay, from week 9, the degenerate example. So we are asked to find point that satisfy this constraint at which the NDCQ fails. Okay, so firstly, we're given this constraint, but this is not of the form that we like. We usually rearrange such that everything with x and y will be on one side and all the constants are on the other side. So we arrange, and then we have y squared minus x cubed plus x to the 4 equals 0. And then this is what we're going to call the constraint function gxy. Okay. And then what is the Jacobian matrix in this case? The Jacobian matrix, well, we have only one constraint, so you have only one row. So grad G. And what is grad G? Well, grad G, differentiate this with respect to x, you get minus 2x squared. Oh, sorry, minus 3x squared. Sorry. Minus 3x squared plus 4x cubed. And then differentiate with respect to y, you get 2y. And then you want this to have rank strictly less than 1. That means that you want this to be a 0. Okay, you want this to be of rank 0. That means that both of this are 0. So for this to have rank 0, we need minus x squared plus 4x cubed and 2y, they both equal 0. Alright? But then this is very easy to solve. You realize that in this case, that means that x equal y equals 0. But then you need to check whether x, y equals 0 satisfy the constraint. But then you realize that in this case, yes, okay? So note, the point x, y equals 0, 0 satisfy the constraint y squared equal x cubed minus x to the 4. So you manage to find a point such that the Jacobian matrix does not have full rank. Therefore, NDCQ fails at this point. And for this reason, this is what we call a degenerate point. So this is what we call degenerate point, degenerate or exceptional point. Because NDCQ fails, okay? So this explains why in this example that we discussed in week 9, why 0, 0 is not captured by the method Lagrange multiplier. Because it fails the NDCQ, okay? That's the reason. So at the end, I want to just mention why NDCQ is very useful for us. So basically, the key point is here. Okay, the key point is here. So if our optimization problem satisfies the NDCQ, then we can use simply just the first order condition to identify all the candidates for the maximizer. So that means that if NDCQ is satisfied, then there will be no exceptional point. Because, okay, and the first order condition would identifies all possible candidates for maximizer. So for the point that maximizes the objective function. And that's why NDCQ is important for us. Because if a problem satisfies NDCQ, we just need to solve the first order condition. And then whatever give out the first come from the first order condition, then we can tell one of them would be the maximum point. Okay? Will give me the maximum point.